So from a week and a half ago, remember we were talking about demand paging. So remember the idea there was we want to be able to do things like run processes in memory that have more than the amount of physical memory we have available, and we want to be able to do things like run multiple processes all at once, which means we have to store all of their memory, but we want to be able to do that potentially with many processes, regardless of sort of the amount of physical memory we have. So remember what we talked about last class with this idea of demand paging, where essentially when you need a page of memory, if you don't actually already have it in memory, you go and fetch it from disk, read it in, and store it in memory. And then we talked about how to do page replacement, remember, which was the idea of when you have filled up all of your physical memory with pages, and some process requests a page of memory that you don't have sitting in physical memory. That's some page that's stored on the disk somewhere, so you're going to have to go get it from the disk and bring it back in. And remember, that's the idea of a page fault. When you have to go get a page from disk and bring it into memory, that's a page fault. And so remember, we talked about a couple of different algorithms for doing page replacement. Remember, so we had FIFO, where we're just bringing in pages and then sort of evicting them in terms of the oldest page we brought in. That'll be the first one we throw out. We talked about the best possible approach that will minimize the number of page faults we get is where we're going to throw out the page of memory that we're not going to need for the longest time, right? And that is provably going to give us the least possible number of page faults given the amount of physical memory we have. But remember, the problem there was that is requiring us to look into the future and see what we're going to request. Since we can't actually do that, we're again, as we did with CPU scheduling, going to assume that by looking at the past, that's going to predict the future. So that's the idea of LRU, least recently used, where you're going to pick the page to throw out that you used least recently on the sort of assumption that that probably is a page you're not going to use for a while if you haven't used it in quite some time. So essentially, LRU is just trying to approximate the best possible approach. So today we're going to talk about, we started a little bit on this last time, but not too much, about how we can actually approximate LRU, how we can actually make an implementation of LRU. And then we're going to talk about how to sort of extend page replacement to multiprogramming, where we actually have multiple processes that are essentially all competing for physical memory. Because essentially, so far, we've just sort of assumed that there's one process with a bunch of pages, and we're deciding how to throw out those pages. So remember, we talked about last time, LRU is a pretty simple idea in terms of it's easy to see how we could implement that perfectly, right? Because if you want what you want to do is throw out the page that you used least recently, then all you need to do is keep track of the last time you used every page, right? So basic way you could do that, just keep a timestamp of every page of memory, and whenever you access that page, you'll update the timestamp. So the timestamp will tell you when you least recently used it, and then when you need to throw out a page, you can just look through all of your pages, find the oldest timestamp, and throw that out. Right, so that's a pretty simple idea. But the problem here is that, remember, we're having to do this on every single memory access. Right, so even something as simple as updating a timestamp, if we have to do that on every single memory access, that's potentially very expensive. Because what that most likely means is to do a memory access, we're having to go to memory to update a timestamp and possibly generate the timestamp and whatnot. So that's very expensive. We can't really do that efficiently. And the other problem is that when there's a page fault, when we have to pick a page to throw out, we have to look through all of our timestamps, right? So that is going to be very expensive as well, to look through all of these pages looking for the oldest timestamp. Now, we could try another approach using basically a linked list to keep track of all of our pages in terms of when we last used them. That would work as well, but still going to be too expensive because the process of updating that linked list is also going to require a bunch of memory accesses. And again, since we're doing this every single time we're requesting memory potentially, we can't really do anything that's going to require even one or even worse, multiple memory accesses. So basically, because LRU is too expensive to do exactly, we want to basically approximate it. So we talked about at the end of last class, the idea of we could basically approximate a timestamp, right? So rather than keeping an exact timestamp, we can basically just keep a couple of bits, maybe a 2-bit or a 3-bit timestamp. And so that's going to, remember we had this idea of, if we have a couple of bits, if we have, 2 bits, then, we could have either a timestamp, 00, 01, 11. And we could say that, this is going to be used in the, these could be pages used in the last 5 minutes, these could be pages used in the last 10 minutes, and these could be pages, used older than 10 minutes, basically. So if we had something like this, then the point is basically that we don't need to have exact timestamps, because all we basically want to do is throw out a page that we're not likely to use in the near future. So if we have a page that is reasonably old, even if it's not the absolute oldest, that's still probably a reasonable approximation. Now, in practice, OSs basically make this pretty straightforward in that we're just going to use a 1-bit timestamp, right? So every page is going to basically have a timestamp of 0 or 1. So this is the idea of the second chance algorithm, where we're going to add a reference bit to each of our pages, right? 1 bit. So the idea is we're going to keep all of our pages in a circular list. So we're going to have a bunch of pages in some circular list. And each one is going to have some reference bit, 0 or 1, just giving some arbitrary values. And essentially, the reference bit says whether that page was recently used. Right? So the way we're going to do this is when you are actually referencing one of these pages, you're going to set the reference bit to 1. Right? Because as soon as you referenced it, you know that that was a recently used page. So you set the reference bit to 1. And then when there's a page fault, remember now our job is to pick some page we want to throw out so that we can replace it with the page that was requested. So the idea here is, again, these are sort of like a 1-bit timestamp where the values are either recently used or not recently used. And so we're basically going to start going around this list. So this is sort of like a clock, where we're basically going to go around the list looking for a page with a reference bit of 0. Right? So if this is the first one we check, then this is a reference bit of 0, meaning we haven't recently used it, so we're going to throw it out and bring in a new one. Now, supposing this was a 1 to begin with, then we start here. This is a reference bit of 1, so that was recently used. So we're going to set that to 0, and then move to the next position. This is still a 1. Set that to 0. Move to the next position. This is a 1. So essentially, we're just going around, setting all the reference bits to 0, and as soon as we find a 0, then that's the page that we're going to pick. Make sense? Basic idea? Right, so this is basically just like a clock, where we have a bunch of frames and each one has 1 reference bit, and you just go around in a circle looking for a 0, and as you go around, you're flipping the 1s to 0s. Yep. Sure. Oh, do you have a question, or you just wanted to see something? Okay. Any questions? Yes.
Do you start at the same point every time, or do you start at different points each time you reference it?
Right, so every time the clock hand moves, it's basically staying there, right? So the clock moves when you have a page fault, right? So your process is executing, and it makes a memory request, and that causes a page fault. So now the clock starts moving, and at some point, the clock gets to a 0, throws that page out, brings in a new one, and of course, when you bring in the new page, the reference bit is, of course, 1. And now the clock essentially stays there until the next page fault, when you're going to pick up right where you left off. Yes?
The clock can only move one direction, right?
Yes. Right. Yeah, I mean, it doesn't matter which direction it moves, but you'll always move in the same direction. Other questions? Okay. Right, so basic idea is pretty simple, where essentially every single page is either a young page that was recently used or an old page that was not recently used, and that is going to be what you throw out. So remember what we're trying to do here is we're trying to get some reasonable approximation of LRU that's not too expensive. So let's consider how well this approach is doing. So how expensive is this when we're just making a regular old memory reference? What are we having to do? Yes. Right. All we're having to do is we're referencing some page, say this one. So we reference this page, we just set it from a 0 to a 1. Right, so we change one bit. And since it's only one bit, we can take that and, say, store it in the TLB. Right, so when we're storing that bit in the TLB, we don't even have to go to memory to update anything. Now that makes it very, very fast. It's one extra bit that's in the hardware TLB, which is very, very fast. So memory access is very, very little overhead in this. Right, so that avoided the main issue with perfect LRU, which is having to go to memory to update some value. And then what's the expense of doing this when we have a page fault? So how many, obviously when we have a page fault, we start running this clock algorithm. Sort of what's the worst case scenario? Yes? Right, the worst case scenario is essentially where every single, if every single reference bit is 1, right, and that could happen. Your program could, reference every single page potentially. So then what's going to happen is every single bit is going to be a 1, so you're going to go around the entire clock setting them to 0. And then once you got to the page that you started at, which was originally a 1, that's now going to be a 0. Right? Because if every single one of these was a 1, if these were all 1s, and say we're starting here, we're going to set this to a 0, 0, 0, 0, 0, 0, and now we're back where we started, and it must be a 0. Right? So we're going to, in the worst case, we have to check every single page. Now, on average, we're probably not going to have to check that many pages because chances are we're going to find a 0 in one of our pages. Right? So it could be sort of as bad as the LRU in the case of having to check every page, though again, we're only having to check one bit in memory, in hardware, so that's still going to be fast. But on average, you're not even going to have to check every single page to find one that you can evict. So one thing to keep in mind is, why is it that when we're running this, our bits are not possibly changing? How do we know that when we are running this algorithm and going around that, say, when we get back to the first bit, which we previously set to 0, how do we know that it hasn't been set to 1 in the meantime? Yes? Right, so during a page fault, you can't reference things, and the reason for that is, remember, what happens on a page fault, we stop running the process. Right, so when a page fault happens, that process stops execution. Because remember, handling a page fault requires going to the disk. And remember, going to the disk is a very slow operation, the order of maybe 10 milliseconds, which in the context of your CPU executing instructions is a really, really long time. So while you're running this clock algorithm, your process is sitting there suspended, so it's not making any memory references. So that's how we know that we're always going to find some page we can evict. And then once we've handled the page fault, remember, we start executing the process again. So, the second chance algorithm is, not as accurate as the scheme where we have sort of a, multi-bit timestamp, because this is sort of even more of an approximation. This is sort of the coarsest way to do a timestamp is to just have 2 values. But, what we get for that is only having to manage 1 bit. So, we can do this in memory. It's very simple and easy to do in hardware. And, we essentially always already answered these questions. We will always find a page, because even if all the bits are 1, we'll just make 1 complete rotation and then find the page to evict. So let's consider one way that we can make this better. So you may recall last class we were talking about swap space. Remember, and we talked about one possible optimization with swap space. Remember, so that was where we could take pages of memory and store them on disk in swap space, where we would when we paged them out, we'd send them into the swap space and then read them back in. And remember, we said that if we have a read-only page, like a code page, you don't actually have to store that in the swap space because it's read-only, so you can always just go back into the file system to find it. So we can basically apply the same idea here with a page that essentially hasn't changed. Right, so let's consider what is the cost of doing a page replacement. So essentially the first thing we have to do is we have to take the page we're evicting and write it out to the disk. Right? Because if we're going to throw out this page from memory, we need to store it on disk so that we can later get it back when we need it. So that's the first thing. We have to write it out to disk. And then the second cost is we have to obviously read the new page in from the disk. Right? So essentially 2 I/O operations, writing the old page and then reading the new page back in. But if we have a page that, say, has not changed since the last time we read it from the disk, then what does that mean in terms of when we're doing a page eviction? Yes. Right. So if this page of memory is stored somewhere on the disk, that page is somewhere on the disk, and if we're throwing out this page, but it's still equal to the copy we have on the disk, then we don't have to do the write when we're evicting it. Right, we're still obviously going to have to read whatever new page we're getting, but we can get rid of the write operation, which is going to be the most expensive part of the page replacement. So, the idea is that the first main idea here is that we want to prefer to page out unmodified pages. Right, because in the simple example where we talked about the regular clock, we didn't say anything about, we didn't really have any information on whether a page was modified or not. But that is actually useful information because paging out an unmodified page is much cheaper. Now, the second idea here that we can use to make this better is that when we have a page that is modified, we might want to obviously replace that page in the future. But we can basically proactively write it out to the disk now, even before we're choosing to replace it. And then in the future, once we do decide to replace it, it will be the same as the copy on disk, right? So let's say that we have this page, and we're not choosing to evict this page right now, but it's it's different from its copy on disk. We could basically just say in the background, let's copy this back to the disk. That effectively makes it an unmodified page, right? Because now it's equal to the copy of the page on disk. So then when later we do decide to evict that page, we don't have to do the write now, which means we're going to handle the page fault faster. Right? Because the whole point is that we want to be able to service the page fault as fast as possible, which means ideally doing 1 I/O instead of 2. Questions on main idea of how we want to make this better? So basically to do this, we're going to, in enhanced second chance, we're going to add a second bit. Right? So here we just had the 1 reference bit. So now we're going to add a second bit, which we're going to call the modify bit. And that's basically going to tell us exactly what we just said, whether the page is basically equal to its copy on disk or whether it's changed since then. So now a given page can have 4 different values based on the value of both the reference bit and the modify bit. Right? Because previously we were just 0 and 1. Now we have 2 bits, so we could have 4 different combinations. So if a page has a 0 reference bit and a 0 modify bit, then what that means is that we haven't used the page recently, and the page has not been modified, right? It's equal to its copy on disk. Right, so that's the best possible candidate for replacement, because we probably don't need it in the near future, so it's safe to throw it away, and the process of replacing it will also be inexpensive, or relatively inexpensive, because we can just throw out the page without having to write it back out to disk. Right, so that's the best candidate for replacement. Now if we have a page with 0, 1, a 0 reference bit and a 1 modify bit, then what that means is the page is not recently used, so we think it's probably safe to throw it away. It's probably safe to not have that page in memory because we likely won't need it in the near future, but it has been modified. Right, so if we chose that page to replace, we would have to first write it out to disk. So that would be, that would take much longer to have to choose one of those pages to replace. Now, if we have, a page that's 1, 0, that means it's a page that we are actively using. Now, it hasn't been modified, meaning it would be relatively inexpensive to page it out to replace it, but chances are, shortly thereafter, we're going to need it again, so we're going to have to go in and get it from the disk, soon after. So that's, not as good a choice. And then, of course, 1.1 is when we have a page that we are actively have recently used and it's been modified, which is obviously the worst possible candidate because it's going to be expensive to page out and we will probably then have to page it back in shortly. Right, so the basic idea in Enhanced Second Chance is we have sort of these 4 classes, and we're going to look for pages to replace starting at the top with pages with a 0 reference bit and a 0 modify bit. Yes?
Does that make everything a lot more expensive just because if, for example, we don't find a 0, 0 and then we have to go through it and look again?
Yes. Great point. So we're potentially, we'll see that in a second, but we're potentially going to have to go through this ring multiple times now. We'll get to that in just a second. Another question?
Would we be able to store them in different tiers? So kind of like the multi-level feedback group, we have different views per se.
Potentially, but remember the whole problem here is that anytime we get into sort of any kind of a data structure, we probably are going to have to store that in memory. Right, and so remember, we could do the basic LRU thing with a pretty simple data structure like a linked list. We could do actual, perfect LRU. But the problem is that if we have any kind of a data structure that is not easily stored in hardware, then we're having to make memory accesses in order to update the data structure, and that's going to be too expensive. Other questions? Okay. So let's see how we actually can do this. So now we're basically going to go around the clock up to potentially 3 times. Right? So now each one of these pages is going to have 2 bits rather than 1. And so we're going to, again, start going around the clock when we have a page fault. Now, if we find a page that is 0, 0, then that's the optimal case, where that's a page we can safely throw out and one that's going to be relatively inexpensive to do so. So we'll just pick that page immediately. Now, if we have a page with 0, 1, remember, that's a page that we're probably okay with getting rid of, but it's going to take a while. So we're not going to pick that page to actually replace right now, but what we are going to do is we're going to start writing it out to the disk in the background. Right, so we're going to keep going around the clock, but while we're doing that, that other page is going to be written out to the disk. And writing it out to the disk is essentially changing that 1 modify bit to a 0. Right, because as soon as that write is completed, the page is now essentially unmodified. Right, so that's basically a page with 0, 1, we're going to do that I/O, and that's going to convert the modify bit back to a 0. But in the meantime, we're going to keep going. Now, the same as in the regular clock, all of our reference bits that are 1 that we're hitting, we're going to set to 0. Now, if we go completely around and we didn't find a 0, 0 page, right, then let's consider what might have happened. So, pages with 0, 1, we essentially converted on the first pass to 0, 0, right? Because we wrote out those pages, and that changes the modify bit to 0. So those pages are now 0, 0. We can take them. Now, we might potentially have to wait for the I/O to complete, right? Because when we're writing out that page, that's going to take a little while to actually do the I/O. Or we might hit a 1, 0 page, an unmodified page that did have the reference bit set, which on the first pass, remember, we set those to 0 as well. And a page that is now 0, 1, remember what that means is that on the first pass, if you have a page that's 1, 1, all you're doing is you're setting the reference bit to 0. So now that is a 0, 1 page, and so you're just going to treat it as you did on the first pass, where you're going to start that I/O and start writing it out in the background. Right, and then by the third pass, the third time around, you're going to have set every single page to 0, 0. So again, you're guaranteed, ultimately, you're going to end up with 0, 0 pages because every pass through, you're setting 1 bits to 0. Right, but see, the way we're setting this up is, a 0, 0 page is obviously preferred because we're going to take that on the first pass if we find one. A 1, 1 page is going to have to wait until the third pass, because on the first pass, we're just clearing its reference bit, but its modify bit is still 1. And then on the second pass, we're not going to pick it. We're going to start writing it out. Right? So this is essentially, this procedure is basically enforcing this hierarchy of prefer 0, 0, and 1, 1 will be the least preferred, which is essentially exactly what we wanted. Right? So let's just do, a simple example of this. So now, we have a bunch of pages with 2 bits, the reference bit and the modify bit. And let's say in this case we have a page fault. So the clock is going to start moving. So on the first page, are we going to choose that to replace? No, right, because it's not a 0, 0. So what are we going to do to that, to those 2 bits? Yeah. Right, so we're going to change that reference bit to a 0. The modified bit's going to stay the same. Move on to the next page. The next page is 0, 1. The reference bit is not set, but the modified bit is set. So what are we going to do with that page? Yes?
Set it to 0, 0,
Right, so we're going to set the modified bit to 0, start writing the page out to disk in the background, and keep going. Third page is a 1, 0. The reference bit is set, modified bit is not set. So what are we going to do there? Yeah. Right, so same thing as in clock, the regular clock, we're just going to set that to 0, and then so on and so forth until we finally get to this 0, 0, and that's going to be the one we actually pick. Right, so the procedure of this is that one gets set to a 0, we do some background writes, we set some reference bits to 0, and after doing these writes, the modified bits get set to 0, and then we actually find the one to replace, bring in the new page. Now, when we bring in a new page, obviously its reference bit is 1 and its modified bit is 0, clearly because we just read it in off the disk. Right? Make sense? Any questions on the enhanced second chance algorithm? Okay. So now let's move on to talking about multiprogramming. Yes.
So is enhanced second chance what's actually used?
Actual systems usually use some variant of LRU, not, again, real systems are usually using these ideas, but with, added things to make them better. But it's the LRU idea is actually used in real systems. So it's not, it's not just to this, but that's the idea used. The, idea of picking least recently used pages and paying attention to pages that are modified or not. So in real systems, actually, the modified bit is often called the dirty bit, which may be a term that some of you have heard before. But that's basically what this is referring to. Something with a dirty bit set is basically saying it's been changed since it was read in off the disk. Any other questions? Yes.
So when both bits are 1, you only change the reference bit, not the modified bit.
Right. Because remember, we're always changing the reference bit to 0, just as in the regular clock example. But 1, pages, right, are sort of the last possible choice we want to make. Because those, we think we're going to need them in the future, and they've been modified, so they're the worst possible candidates. We want to choose them only if we essentially have no other choice. So by leaving the modified bit 1, we're not going to do this right. We're just going to leave it modified. And then it's going to come all the way around, and we still won't choose that if we have to make a second pass. We're going to prefer a page that is either 0, 1 or 1, 0 over a page that's 1, 1. Yes?
So is it possible for the bits to get modified again as you're going around it, or does it just lock it? Because I would think that if it was a bit that was very frequently used, your process could get halted in between the iterations, and then all that work would be for naught.
Well, so remember, this is what we talked about a moment ago, which was that when you're doing a page fault, when you're handling a page fault, your process is never running.
Okay.
Right? Your process is basically frozen until the page fault is handled.
Okay.
Right? Because when you have a page fault, that gets handed off to the OS. The OS basically suspends your process and will not reschedule it until the page fault has been handled.
Okay.
Right? So remember, page faults are completely transparent to the process. The process has no idea that page faults are occurring. It may get stopped every so often while the OS handles a page fault, but the process itself is just executing as usual. Any other questions? Okay. So far we've basically just been talking about what a single process is doing with its own pages. Now, of course, in an actual OS we have multiprogramming where we have multiple processes running, and so the OS, of course, needs to decide how are we actually going to manage memory that is shared by multiple processes. So An important idea here is, remember the idea of the working set. Remember, so when we were talking about why we can essentially run a whole lot of processes at the same time, remember we talked about the idea of the 90-10 rule, that a process most of the time is only accessing a small bit of its memory. Right? And so this is basically why we can run a whole bunch of processes at once, because we can just store the little bits of their memory that they're actively using, which will now allow them to do computation, and everything else doesn't actually need to be in memory most of the time. So now with lots of processes, right, each process has its own working set, its own set of pages that it's basically actively computing on. So if you basically have if you have a lot of processes all running at once, they all have their individual working sets, you may not actually have enough memory to store all of their working sets. And so essentially what this can lead to is what's called thrashing, which is where your memory is basically overcommitted to the point where you're having to throw out pages that are actually still in use. Right, so basically the idea here is this graph is basically showing a picture of what would happen as you increase the degree of multiprogramming, meaning you're running more processes on your OS. And right, so remember why we like multiprogramming is because we add more processes at the same time. That allows us to interleave I/O and CPU, so our CPU utilization is going to go up. But at a certain point, we're basically stuffing so many processes into our memory that they're constantly requesting pages that are not in memory because it's too, it's shared too much, right? So if you have, two processes that each are constantly requesting 3 pages, but you only have 5 pages of physical memory, you're going to end up with a lot of page faults because you are basically your memory is essentially too overcommitted. So what happens is, as you add too many processes, you're going to get thrashing where all of a sudden you start getting a lot of page faults. And if your process has a lot of page faults, then you're basically not getting any work done, and your processes essentially become I/O bound, right? Because page faults take a really long time because they're doing disk I/O. So your CPU utilization is actually going to fall because all your processes have essentially become I/O bound and can't do any more computation, right? So you may have you can actually see this on your own machine. I think it's less common than it used to be since typical machines nowadays have lots of memory. But you certainly may have seen points at which your computer suddenly got really, really slow, and it sounded like the disk was working really, really hard, and your programs were not really responsive. And that's basically a symptom of thrashing, where you are constantly, reading and writing pages to the disk, and because all of your processes are waiting for that, and the disk is really slow, essentially your whole system bogs down. Right, so this is the main thing that we have to avoid when we're talking about multiprogramming, because we still have a fixed amount of memory, and we need to be able to contain enough, we need to have enough memory for each process that's running that they can actually still get work done and not thrash. So what would be one really easy way to deal with this? What would be sort of the easiest way to prevent this from ever happening, prevent thrashing from ever happening? Yes. Well, more memory. That's true. You can always add more memory. But assuming you're not adding more memory, what could your OS do? Sort of any sort of restrictive policy. Yeah. Right. You could essentially just say, the problem here is when we have too many processes and we can't, don't have enough memory for them, so we can basically just, not allow so many processes to be created. Now, if we recall from CPU scheduling, we had this idea of short-term scheduling and long-term scheduling. Long-term scheduling was basically where we were sort of picking the set of jobs to run to completion. We could do something like that where, your computer, you might have 100 processes wanting to run. Your OS might say, well, that might lead to thrashing, so I'm just going to pick 10 of them at a time, load those into memory and run those, and everything else will just wait, right? And that will obviously decrease at any one time the amount of, the amount of memory that you actually need. So, that's sort of one easy way to deal with it, but obviously we'd sort of like a more flexible way. So, ultimately what we want to do is give each process enough memory so that it is not going to thrash, right? And so the OS is basically going to need to decide this via some kind of replacement policy that's aware of the fact that we have multiple processes, and if we're not smart, we might actually cause thrashing, right? Because we don't know ahead of time how many processes there are, so there might be a huge amount of pressure on our memory. So one sort of approach that's sort of the easiest to consider in the context of what we've already talked about is global replacement, where we essentially have one huge pool of memory, and let's say we run LRU on the one huge pool. So we have one LRU queue that has all of the pages from all of our processes, and we just do that. So advantages of that are a process can potentially get all of the memory of the machine, right? So it's sort of very flexible because a process that needs a ton of memory can actually get a ton of memory. But the downside to this is that this may actually make thrashing more likely. So why is that? Yes.
If the processes are queued up in order, and the least recently used process might be queued up next, but its memory is also the least recently used, so it's also the most likely one.
Right. So basically, processes can interfere with each other because there's essentially no isolation here. So you can have a process that is running and basically claims all of the memory. This is an extreme example, but you could have a process that claims all of the memory, and then another process starts to run, and it tries to claim all of the memory, going to get a ton of page faults, and in the process going to evict all of the first process's memory. Switch back to the first process, start running, and again, everything is paged out, so you hit a ton of page faults. Right, so essentially the problem here is that there's no isolation between processes, and so sort of any process that either is misbehaved or requires a ton of memory can negatively impact other processes, even if they don't require a lot of memory. Right, so not exactly ideal there. So instead what we can do is per process replacement, which means that we're essentially going to give each process a set number of frames. Right, and then within each process, we can essentially do this regular scheme where you as a process have some set of frames you can use, and you're going to do your own LRU on your pages. You'll page your own, you'll replace your own pages in memory, and of course, you'll keep your most frequently used pages in memory, and you'll throw out others, and that will not affect any other process because other processes have their own frames of memory dedicated. Right, so advantages of this are, well, of course, this also means that we are, sort of splitting up our physical memory. So we're only going to be able to run processes that we sort of actually have some allocation of physical memory to give. But advantages of this are, right now we do have isolation. So one misbehaved process could be using a ton of memory, but the only process that's potentially going to harm is that own process because it, may cause a lot of page faults of its own memory, but it's not going to evict other processes' pages. Now, disadvantages are, right, if we take our memory and we sort of just split it up without sort of thinking about how we're splitting that up, then potentially we may have a case where we have one process that, say, only uses a little bit of memory, but has a lot allocated to it, and another process that needs a lot of memory doesn't have enough allocated to it and is therefore getting a lot of page faults, right? And that's essentially wasteful because we have some unused memory that we'd rather give to some process that actually needs it, right? So the main question here is, how do we decide how many frames to allocate each process, right? So the natural approach, the most obvious approach is to just divide it evenly. If my machine has 2 gigabytes of memory and I have 4 processes, then I'll just give each process 512 megabytes of memory, and that'll be that. Right, now that's pretty naive, so actually a better way to do this, it's only a little bit more complicated, is what we call proportional allocation, which is we're going to give more frames to large processes, right? So a process that has a huge heap or a huge stack that's using a lot of, that has a lot of data, we'll just give more physical memory to a process like that. Right, so we can basically say that the allocation for a particular process is going to be the size of that particular process divided by the size of all processes. Right, so this is basically just a ratio. So if we have, if a process is, if we have say 3 processes, and the first process is equal to the sum of the second and third processes, then the first process essentially gets 50%. Right, so this is essentially just a proportion of the entire process size, the size of all processes, times however much physical memory you have available. Right, so this is just going to say large processes probably need more memory, so we're going to give them more physical frames to use. Now, this is still largely a guess, right, because this is basically saying if you have a process that has a ton of data, then you're going to need a lot more memory to actually run. Right, but we can think of a really simple example where that might not actually be a good guess. Right, you could have a process that, say, allocates a 1 gigabyte array, for example, allocates a ton of memory, and uses it once, and now just requests the same page over and over and over again until it's done. Right, and if that's the case, then you probably don't want to give that process a ton of memory relative to some other process that maybe is not as large, but still is actually working with a larger number of pages. Right, so this is essentially just guessing that a large process needs a lot of pages to actually do its work. So what is the amount of memory that we actually want to give a process? So remember, what is it that we talked about that basically says how much memory a process needs at this time to do its work? Remember, this was the idea of the working set. Yes? Right. So this gets, again, to the 90-10 rule, where you have a small set of pages that processes are accessing very frequently. And we want to be able to store the working sets in memory, and that will allow the process to make progress and not encounter a lot of page faults. Right? So, the idea is we want to give each process enough frames for its working set size, which, as I just gave a simple example of, the working set size may not actually correlate with the size of the process. Right? You could have a process that has a ton of data but actually has a very small working set if it's accessing a small amount of memory repeatedly. Right, so actually another thing is we can remember from last class when we were talking about LRU, and we constructed that simple example where LRU did really badly. So remember we had an example there where we had 3 frames of physical memory, and we're accessing memory like this, A, B, C, D, A, B, C, D, so on and so forth, just A, B, C, D over and over again. And remember we sketched out how this does really, really badly with LRU because, right, you do A, B, and then C into your 3 frames of memory, and then D is a page fault, so you throw out A. Then A is a page fault because you throw out B. Right, you're essentially every single access is a page fault. And remember the reason for this was basically that if your memory access pattern is A, B, C, D repeated over and over again, what's the size of your working set? Yes. 4, right? If you're requesting A, B, C, D over and over and over again, then your working set is all 4 of those pages, right? So if you don't have enough physical memory available for that, you get a ton of page faults, right? So that's basically just what we're saying here, is that in order to avoid getting a lot of page faults, each process needs to have enough frames for whatever its working set size is. So we sort of define working set sort of informally as the pages a process is currently using while it's executing. But sort of more formally, you can basically define the working set as the pages that the process has referenced in some past period of time. Right? So we could say that in the past 5 seconds, process A referenced 10 different pages of memory and process B referenced 100 different pages of memory. Right? And then you might just say that, process B therefore has a working set size of 100 pages, process A only has a working set size of 5 pages. Right? So, of course, the question here is then how do we actually pick T? Right? What is the size of the interval over which we want to call that our working set? So, one thing that's useful to consider here is, again, how long a page fault takes. Right? So one page fault to service requires going to the disk and is going to take on the order of 10 milliseconds or so. Whereas in 10 milliseconds, you can service 2 million instructions. Right, so clearly you basically need your working set to be much larger than, you need your working set to be large enough to handle a lot more than 10 million instructions, right? Because essentially if you're getting a page fault every 2 million instructions, say, then you're basically spending 50% of your time page faulting, right? Because every 2 million instructions takes roughly 10 milliseconds. If you get a page fault every single every 2 million instructions, then you're basically spending half your time page faulting, right? So you basically need T to be a whole lot bigger than, you need T to be large enough that you don't hit a page fault in a lot more than 2 million instructions. So, if T is too small, then you basically spend all of your time page faulting. What's the problem with making T sort of arbitrarily large? Right, so let's just say that I'm going to make my working set, the pages used in the past 3 hours. Yes?
It would be functionally the same as saying the working set is all of the process.
Right, exactly. So as you make T bigger, you're including more and more of the pages of your process. If you make it sort of arbitrarily large, then your working set is basically all of the memory of the process. And right, if we're doing that, then we're essentially destroying the entire point of demand paging and saying we have to keep the entire process in memory or we don't have room for it. Right? And our entire objective here was the working set is much smaller in almost all cases than the actual process, and we only need to store the working set. Right? So we basically need to have a balance of a working set large enough that we get few page faults and spend most of our time doing useful work, but not so large that the working sets become very, very large and we don't actually have room to store all of our processes in memory. So let's consider how we can actually determine the working set, right? Because now we have the issue of, this nice issue of the working set. That's how many pages we want to give. That's how many frames we want to give to a process. We, of course, now have to ask the question, well, how do we determine what the working set actually is? Right, so this basically shows up here what the working set would actually be for some specified interval that we can basically define the interval in terms of a number of memory accesses. Right, so the working set could be the past 10 memory accesses or the past 20 memory accesses. So if we have this process running, these are the sequence of memory accesses. And so if we're right here and this is our working set interval, then the working set is basically every page referenced from here to here, which is 1, 2, 5, 6, and 7. Obviously, a few pages are repeated, so they're not duplicated in the working set, obviously. So working set size here is 5, versus if we're later repeatedly requesting, in this case, just pages 3 and 4, then the working set size is 2. Right, so that would be how you would actually keep track of the working set size. But problem here is exactly the same problem we had. Yes, question?
Yeah, is it on purpose that the 6 is not included? Or was that
Well, there's a 6 here. This one?
the second 6? Is that included in the working set for the second? Is that just-
Well, so
am I
here,
not-
right, so we're looking at this interval, and all we've requested is 3 and 4.
Not the 6 right after the first interval? At the end of the one? Okay, never mind.
So
Never
this
mind.
this is the interval over which we're calculating the working set. Right, so we don't consider any memory accesses that are outside of that interval. Right, so we requested 6 previously a while ago, but at this point, when we look back at this interval, right, this is the interval we've defined that basically is going to say what our working set is. All we've seen is 3 and 4, and we haven't requested anything else. So, again, the problem here is that we can't really do that exactly because we're again going to have to basically write memory on each memory access in order to keep track of what the working set is. Right? If we're going to maintain these potentially very large working sets, because the working set could be a lot of pages, there's no guarantee on how small that might be. So we would have to go into memory to do that. And again, that is basically meaning we're having to go into memory in order to make a memory access. And right, just as with LRU, that's essentially a non-starter. So instead, we need some other approach that will allow us to again, as usual, we're going to try to get some approximation of the working set. We're not going to be able to do it exactly. So one approach is to basically just sample, right? So we're making all of these memory requests, and we could basically just say, well, let's just pick a small number of our memory requests and assume that that's representative of the working set, right? So let's say, let's just pick every 1,000th memory reference and actually do the bookkeeping to keep track of what the memory access was and keep track of the working set, right? And if we're only doing that on every 1,000th memory access, then it's not going to slow us down nearly as much to do that. And over the long term, the idea is that you're going to be, again, accessing the same pages repeatedly. So if you're sampling every 1,000th reference and you keep seeing the same page over and over again, then that's basically going to result in a small working set. Yes?
Did you already have allocated the appropriate amount of memory for it to run before you can determine what the working set is? Or are you changing the size of the memory it's allowed to run on?
Well, so remember, the working set is essentially completely separate from the amount of memory that the process itself has allocated. Right? The process is allocating pages of data to itself. But the working set is referring to what the process is actually using as it runs. Right? So again, we could have this sort of simple example. If a process allocates a massive array and then repeatedly accesses one element of it, and that's all it does, it will have allocated itself a lot of memory, but the working set is actually only the one page.
Yeah, but I thought we were using the knowledge of the working set to change the size of the memory allocated to the process.
Well, we're changing the number of physical frames that the process has. But the process itself is allocating virtual memory, right? So the process itself is allocating pages of data, and those are stored either on disk or memory or both, right? So the process itself doesn't know anything about whether its data is actually in memory or stored somewhere on the disk. Right? This is all, again, happening completely transparently to the process itself. The process allocates memory and thinks it has memory, but it may actually just be data sitting on the disk until it tries to use it, at which point it will be swapped in. Does that answer your question? Another question?
So at first, it's like when a new process starts, we can track those thousand processes.
You mean if we're doing a sampling approach?
Yeah.
Right. So I mean, a process will start running and it will start issuing memory accesses, and typically a very large number, right? Because a memory access is done all the time, right? Constantly.
And then
So
after that, basically the working set, like those algorithms, is active, right? And that it will determine how much space needs to be left for what it did after those 1,000 frames, or rather those 1,000 memory references.
So I'm not sure I understand your question. So all we're doing in building up the working set is basically trying to give some measure of how many frames of physical memory the process actually needs to run effectively. Oh yes, it would be the last, you take some, the last number of samples, and that would be changing over time. Yes, I think is that your question? No, this is basically just this is actually not used, but this is just sort of a simple way we could try to do this. Now let's actually talk about the better way that we can actually do this, which is, a better approach is to basically actually track the behavior of the process. Remember, because again, our objective here is minimizing the number of page faults, right? So if we're getting a ton of page faults, clearly the process needs more memory than it has in order to be able to run effectively. And if we're getting a ton of page faults, that's basically a good indication that its working set is not contained all in memory and it needs more. So basically we can set two thresholds. So we're executing our process, and each time there's a page fault, we're going to just increment some counter. And if we get too many page faults, in some specified period of time over some threshold, if we get some page fault frequency that's above a certain level, then that's going to be an indication that we want to give it more frames. And if we have a process that has very, very few page faults, then that's probably a pretty good indication that the process doesn't actually need all of the memory that's been allocated to it. Right? Because you are expecting to get some page faults. If you don't have any page faults, then probably there's not going to be too much harm in taking away some of your frames. So the idea here is that, right, we expect to see something like this, where as you add frames, initially when you are basically thrashing and doing page faults over and over again, you add frames and your number of page faults will drop dramatically. And then if you sort of add more and more, you're basically getting quickly diminishing returns where maybe you were getting a few faults previously and now you're getting none, but that's sort of that's not a particularly great advantage. So we basically just want to keep everyone out of this area where you're faulting a lot. So if we ever get a process that's up here, we can basically take frames away from a process that's down here. Right, so we're then going to basically just be adaptively swapping frames between processes that don't appear to need them and processes that do appear to need them. Trying to get everyone here where they're getting probably a few page faults, but not so many that it's actually significantly degrading performance. Now, essentially the goal here is we basically want the system to be able to handle page faults continuously without backing up. Right? Because if the system has a ton of page faults, then what we saw in thrashing is basically where everything stops being able to do work because it's waiting on the disk, right? Because everything is waiting on a page fault to finish. So what we essentially want is the system to be able to handle all of its page faults without actually holding up any other processes. So the goal is to basically make the time between page faults equal to the time it actually took to service the page fault. Right, because then you basically have the best utilization because every time you finish servicing a page fault, you have another one ready to go, but you never have a list of processes that are all waiting on the disk and blocked, doing that I/O. Right, so there you're essentially maximizing, both CPU and I/O utilization. Now, of course, again, if you sort of throw too many processes at this, too many memory requirements, or if your working sets do not physically fit in memory, then you may end up in a situation where sort of everyone is up here, and there's no one down here that actually has frames to give up. So if you want to make sure that everyone's here, then you may actually need to suspend processes in order to actually free up their memory, right? But this gives you sort of a reasonably easy way to do that. If you see everyone is up here, then you can basically just pick a process and suspend it, free up all of its memory, and do that until everyone is sort of out of the upper bound area. Right, so that was just basically a simple way that you can avoid thrashing by actually keeping track of, essentially, we're looking for thrashing type behavior and then preventing it if we see it. Questions on how this is working? Okay. So, yeah, so also let's remember again, efficiency was sort of the main consideration here. So, let's consider the efficiency of this. What are we sort of doing? What's the overhead of doing this approach? So remember, when we're talking about overhead with these replacement schemes, we're essentially talking about what's the overhead when you're doing a memory access and what's the overhead when you have a page fault. Right? So what's the overhead of this for regular memory accesses? Yes? Yes, page faults. Yes. Yeah. So memory accesses, there's basically no overhead. Right? You don't have to track anything. So that's good. And a page fault, all you have to do is basically increment some counter. So that's also very inexpensive. And remember, page faults are happening really, really infrequently. Remember, we did sort of some back of the envelope calculations last time where we said sort of how many, if you are willing to take, a 10% slowdown, I don't remember the exact number, but it was something like, 1 in, 100,000 memory accesses could be a page fault and no more. So page faults are very, very infrequent. So, minimal operation done very infrequently, this scheme is very, very cheap to implement. So, advantages of this, thrashing is less likely because we're still getting that isolation between processes, right? We're not allowing processes to trample on other processes' pages, but we are still getting, that adaptive behavior where processes that have larger working sets will get more memory if memory is available for them. Now, of course, we're getting a little bit of added complexity in that we're having to figure out how to do that allocation, but we see that we can do that pretty inexpensively. So now I want to talk a little bit about kernel memory. So everything that we've talked about so far basically is just pertaining to user processes. So we, of course, also have to allocate memory to the kernel itself. Right? The kernel itself is using memory to store all of our OS data structures, all of our process control blocks and page tables and all of that is all being stored somewhere in memory used by the kernel. And basically, the kernel doesn't use any of these kinds of memory management techniques that we've been talking about. So, for example, the kernel doesn't really use paging. Now, can anyone think of why it might be a problem if the kernel was to use paging? So, Right, exactly. The kernel is in charge of actually doing the paging. So, there's some code in the kernel that basically says how to do a page, how to handle a page fault, how to do the swap. And if you get a page fault in the kernel and the code page that has, the code to actually handle that is swapped out, then, what do? You essentially can't handle that. So the kernel basically needs to have sort of a more direct access to memory because we actually rely on the kernel to basically keep all of our memory management algorithms actually running. So, the kernel doesn't use things like paging. Now, the types of memory allocators used by the kernel are actually also used by user programs or libraries. So, for example, in C, when you're writing a program in C and you say malloc, right, that's basically calling some memory allocator algorithm that's actually fairly similar to what the kernel uses. But there's a lot more details on this in the book that I'm not going to go into, but I just wanted to briefly mention sort of the two main types of allocators that the kernel uses. So the first type is what's called the buddy allocator. So the idea here is that the kernel is requesting memory. The kernel needs memory to store things, like PCBs, for example. And the kernel could request any arbitrary amount of memory. But in the buddy allocator, what we're basically going to do is we're always going to allocate memory in sizes of powers of 2. So, as a simple example, let's say that the kernel requests 513 bytes of memory. So we're not going to allocate 513 because that's not a power of 2. The next largest power of 2 is 1024. So we're going to allocate a piece of 1024 bytes, of which this is going to be using let's say this is 512 right here, and this is 513. So we're just going to allocate 1024 bytes, and this is going to be used that's going to be used by the kernel. And now we have this leftover piece. But what we can actually do is, in the buddy allocator, we're basically going to be able to take our memory and keep splitting it into other powers of 2. Right? So this piece right here is not a power of 2, but we can basically split this so that there's another 256 bytes here. And then there's, this is 256 bytes, of which one is being used by the piece of data we allocated to the kernel. So now we're using this 513 and this 256, and then there's this block of unused memory, which is not a power of 2. But we can again split this so that we now have 128 bytes here that we can use. So basically the idea here is that we can just allocate blocks of memory in powers of 2, and in order to use that, when we, in order to not waste all of the extra, we can just keep splitting it in half in order to get other powers of 2. Right, so essentially if we keep splitting this in powers of 2, we can basically use up all of the memory, and what we're allocating is all powers of 2, which means that if I request, 250, let's say I request 253 bytes of memory, that means all I need to do as the OS is look for a block of 256 bytes, And so you essentially can just keep, lists of these are the blocks of, 256 bytes or greater that I have. So this is kind of like, in paging we were dividing everything into fixed size pieces of memory. Here we're dividing everything into powers of 2, right? But there's only going to be a few of those, right? Because you're not going to have 10,000 different block sizes if all of your blocks are powers of 2. Right? You might have, maybe 10 or 20 different block sizes, but it's still a pretty small set. So whenever you need a block of memory, you're just going to allocate in a size in a block of a power of 2, and you can always take your memory and chop it up into smaller blocks to actually allocate it pretty efficiently. Right? So we do still have some internal fragmentation where we sort of have this extra block, that the extra bit that's not being used. But by continuing to split that, we can essentially prevent fragmentation from being a serious issue. Right? And with this approach, we're not going to have external fragmentation at all because we can always just allocate another power of 2 block. So that's the buddy allocator. The other type of allocator I want to mention is what's called a slab allocator. So the idea here is basically that you're going to allocate blocks of memory that are used for a specific object type. Right, so let's say you have, a PCB entry uses a certain amount of memory, right? The kernel is allocating PCBs, and they each use a certain amount of memory. So you're basically just going to say in the slab allocator, okay, give me a big piece of memory, which is called a slab, and I'm going to use that for PCB entries. So the kernel basically hands you a big piece of memory, like an entire page, for example, and you can basically just split that up into pieces of whatever the data size you're using is, right? So I can basically just get, this big piece of memory. This is going to be my, slab used for PCBs, and I can just, split this up into entries used for, each one of these will have, a PCB entry. And then, right, you can fill things in as you deallocate things. You can obviously fill them in with new PCBs, right? It becomes very easy to sort of allocate and deallocate memory when everything is, everything you're using in the slab is an object of the same size. Right, so basically what the slab allocator is just doing, and this is actually used in Solaris and Linux, is getting a bunch of slabs that are used for specific data types, and then just reusing those slabs as they execute. Right, so again, you're directly getting memory here. It's not, the paging approach, but, these are how the kernel actually uses memory without getting serious difficulties due to fragmentation. So this is pretty high level picture, but there are a lot more details on the book if you're interested. So last thing I wanted to talk a little bit about was page sizes. Right, so we've talked about pages a lot, but we haven't really said anything about, or haven't said too much about sort of what determines how big we actually want to make our pages. Right, so what might be some reasons we'd like to have really small pages? What's the advantage of having really small pages? Yes? Right, decrease internal fragmentation. Because remember, what we're doing when we're allocating pages is, that's sort of the minimum amount of memory we're allocating. So if, your process needs this amount of memory, but a page is this large, if this is the process, and a page is this large, right? This is all internal fragmentation that's basically being wasted. Right? So the smaller you make your pages, the less internal fragmentation you have. Right? Because if your page is, this large, then you'll just allocate a bunch of these pages, these tiny pages, and you might only have, a tiny bit of internal fragmentation for this process. Right? So smaller pages means, less internal fragmentation. As a result of that, you're basically making better use of your memory, so you can run more programs, higher degree of multiprogramming. Now, why might you prefer large pages to small pages? So how about overhead? So how is the overhead of your system going to change? Yeah.
With a large page, you only need to load it once, so you're reducing the number of page faults, rather than with smaller pages, you're going to have to be loading a lot of them, looking them all up in a page table.
Yeah, so that's a very good point, is that in general, right, remember we have this idea of locality, which is that you're typically requesting data in the same area over and over again. right? So if you're loading a larger piece of data all at once, chances are you're loading useful data that you might actually request in the future. Whereas if you were requesting a very small page, you might then ultimately end up with more page faults to get the little pages around that one, right? So if we have a bunch of data here, if this is our one of our pages, and we're requesting data, we request here and then here and then here, that's going to be a page fault because we'd have to go fetch the next page. Whereas if this were a much larger page that we previously loaded in, then that's not going to be a page fault. So fewer page faults is one advantage. Another one that was mentioned was you're looking this all up in a page table, right? So if you have very large page sizes, then you have a much smaller page table, right? So there's going to be less overhead in actually managing the page table. And another one is actually that it's basically going to mean that the overhead of going to your disk is going to be less, right? And so the reason for this is that, remember we said that you're spending maybe 10 milliseconds to go to the disk. Now, let's say you get a page fault and your page is 1 kilobyte. So you go to the disk and you read 1 kilobyte, and that takes roughly 10 seconds. So what if your page size was 8 kilobytes? You go to the disk and read 8 kilobytes. That's going to take about the same amount of time, right? Because basically most of the time you're waiting is basically for your disk to find the location on disk that you're reading, not to actually transfer the 1 kilobyte or whatever the page size is. So with larger pages, you're actually going to spend less time waiting for the disk because it's essentially the same amount of time to read 1 kilobyte or 8 kilobytes or 20 kilobytes. So in actual systems, page sizes are basically growing on the whole. Now, one reason for this is that physical memory is really cheap. So with a lot of memory, you can have a really huge page table if you have small pages. And also, remember the big advantage we got from small pages, which is less internal fragmentation. If you have a ton of memory and you don't really care about squeezing every bit of efficiency out of your memory, then smaller pages is not really an important issue. So another reason is basically that CPUs keep getting a lot faster. Disks have essentially not gotten so much faster to the same degree, and so as a result, really decreasing page faults is sort of the number one concern. And so as we said, larger pages will tend to result in fewer page faults. So typical page size is sort of 4 kilobytes is sort of a ballpark figure, but many systems have increasingly been increasing that. I think, as I recall, I think Solaris actually used 2 different page sizes. They could allocate, I think, 4 kilobyte pages and also, I think, multi-megabyte pages for processes that wanted them. So basically, to just summarize what we've talked about in page replacement, so remember, the main objective here is page replacement is letting us run all of these processes at once without having the physical memory to store all of them in memory at the same time. But remember, the main objective is we need to be able to do that while still avoiding thrashing. Because if we just sort of throw everything into memory all at once and use one of our page replacement algorithms, if we have a ton of page faults, essentially, no matter the algorithm we use, we're going to do really badly if we get into a position where we're thrashing, because we're just going to spend all of our time waiting on the disk. Now, if you have a ton of physical memory, and you can basically just store everything in memory, then essentially your page replacement algorithm is optimal regardless of the choice, because you're just going to load everything in once you need it, and then it will just stay in memory. Right? So the choice of the page replacement algorithm is basically important when you do have enough memory that you can keep the working sets in memory, but don't have so much memory that it doesn't even really matter how you're doing page replacement. And then we talked about how the key issue with sharing processes and multiprogramming is that the OS needs to decide how to allocate the frames of physical memory to each of a large number of processes potentially. That's pretty much everything I wanted to cover. I just wanted to mention briefly that there's actually an allocator, a memory allocator called Horde that was developed here at UMass by Emery Berger. And basically, this is actually the memory allocator that's used in the most recent version of the macOS operating system. It basically is a similar idea to the slab allocator we talked about, but it's essentially targeted at being really, really fast, especially on multi-core machines. So that's basically provided as like a built-in, it's like a replacement for a malloc routine that you might have on your machine. So obviously, if that's of interest, there are papers on that. But I think let's stop there. So that's pretty much it for memory management. So next class, we're going to start on the third major topic, which is file systems. And then after that, we'll still have networking to talk about a little bit.